alcohol altogether. This particular alcohol is known as phenol. It's an alcohol with a benzene ring attached to it. And you haven't really learned about aromaticity. You won't till next semester, thank God. I don't have to teach you this, and you don't have to think about it for a while. But this benzene ring is kind of special. It has lots of pi bonds in it, and you should have at least been introduced to it in the context of resonance. We're going to do the same reaction with water. We're going to compare this to methanol or ethanol. pK of 16. And we're going to talk about the pK of phenol, and we're going to see something different about it momentarily. But let's practice the acid-base reaction between phenol and water. In all the compounds and cases we're doing this equilibrium reaction with, we're considering this is the acid, this is the base. So in each case, we start our arrows from the base. They go towards the acidic proton. This bond breaks. We have some equilibrium process here. We have to draw with some level of caution and care, some fidelity. We have to be able to draw the conjugate base and hydronium ion. We should be getting bored of it right now because we've drawn it 4 times already in this class. But we should be able to draw this quite quickly. And the question is, which of these two species is more stable? Well, turns out the pK of phenol, this is what I want you to memorize, is 9 or 10. We'll use 10 this semester. This is an additional one I want you to memorize. It's not just a simple alcohol. It's actually quite different than ethanol. pK drops dramatically compared to ethanol, and we'll briefly introduce why through invoking resonance. First glance, they don't look too terribly different. You have an OH bond, an OH bond, next attached to carbon. So we have a lot of similarities here. We learned a little bit about the inductive effect. Not the inductive effect, the hybridization effect, which we'll talk last about in this class. But in short, this is hydrogen, oxygen, carbon, hydrogen, oxygen, carbon. Not too much difference, but when we compare these two things, this particular entity is significantly more stable due to resonance. It can be resonance stabilized, where we learned about resonance with Dr. Martinez. This negative charge can be distributed and shared across multiple atoms. Well, we could just practice resonance a bit. Some of you were quite rusty on it on the first exam. You don't like resonance? Well, resonance is going to come back over and over again until you do like it and do get good at it. So it's better to get good at it than wait around forever. But this negative charge, one thing we can do is we can distribute it to other atoms. Well, we could push it this way. This will make a 5th bond to carbon. This bond can break. And we could draw this is a resonance structure. We could continue this operation. And we could draw another resonance structure. And where I'm coming up with and how I'm putting these bonds and lone pairs of electrons follows from that blue arrows that I'm using. And your knowledge of resonance should be enough for you to understand these. Maybe not draw these, but what you've learned about resonance thus far, you should definitely be able to understand what I'm doing in front of you. Maybe not do it yourself, and that's okay for me. But resonance actually is distributing this negative charge across multiple atoms and sharing it. This particular conjugate base of phenol, called phenoxide, it has resonance stabilization. So this helps explain in this particular molecule why the pK is 1 million times, or the acidity, this is 1 million times more acidic than this, 6 zeros. 1 times 10 to the 6, Ka. It's 1 million times more acidic. This difference of 16 to 10 is a negative logarithmic relationship, so it's really 1 times 10 with 6 zeros after it. Much more acidic, and we can rationalize that if we look at these two, that this has stabilization of negative charge, this does not. And if we can stabilize this reactive species, then it's easier to break this bond in the first place. This is kind of a weird circular logic, it might seem to you, or not quite making perfect sense, but using this tool by taking a new acid that we're exploring and trying to understand why its pKa might be so different, we just react it with water, we draw the conjugate bases, and then we can compare two conjugate bases, see if there's any stabilizing events, and that can help us backtrack and understand why there's a difference here. We're going to talk about the energetic basis of where this comes from right now. It's called delta G. It's a thing that you learned a little bit about in general chemistry. Again, we don't do calculations. We don't have to do calculations in this class, but we're going to talk about delta G and its relationship to K. General equation for this is delta G equals RT log K, or natural log of K, and K is our Ka or KEQ, and delta G is the free energy difference between reactants and products. So this is free energy difference between reactants and products in a reaction can be related to the equilibrium constant K. So the free energy between reactant and product is related to, by this particular equation, K. What we're going to do is draw a relative energy graph, and we're going to do lots of these this particular semester. So this will be our first, we have this as our first relative energy curve. Okay, we're not going to deal with absolutes necessarily for now, but we're going to just start with some energy level down here. And the first one we're going to do is we're going to look at ethanol, molecule we spent a little bit of time with so far, and ethoxide. This is the acid conjugate base pair for ethanol. We worked with it already. And this is the rough or relative energy gap between these two for our discussion. To go from here to here requires a significant amount of energy. This is much more stable than this one. Higher in energy, it's less stable. That's what this graph is meant to illustrate. This particular energy difference turns out to be about 21.7 kcals per mole. That probably doesn't mean anything to any of you. That's absolutely okay. But it means the Ka for this reaction is roughly 1 times 10 to the minus 16. Means the pKa for this reaction is equal to 16. Okay? So the Ka for this particular reaction in water is 1 times 10 to the minus 16. Means this doesn't happen very much. Means the pK of ethanol is very close to water. It's not very acidic at all. And the energy difference, the delta G, is related to Ka. If we plug this into this equation, we'll get these two numbers matching up with one another. So this doesn't make perfect sense just yet, but let's actually take phenol, the molecule we were just working with. We're going to plot it right at the bottom here. I guess I didn't leave myself enough space. It's okay. We'll put phenol here. That's meant to represent this line here. And then we'll put phenoxide up above it. And this is the energy level of phenoxide. And phenoxide, or phenol, the pKa, was equal to 10. The energy difference between here and here and here and here is different. And it's not drawn linearly or perfectly to proportion. The point of this graph isn't to have perfect mathematical accuracy here. The point is to illustrate on a graph that it's easier to pull off this proton and make this unstable species than it is to make this one. And that is definitely due to resonance. These are both unstable species, but the gap from acid to conjugate base requires much less energy to bridge, means it's easier to break this particular bond than it is to break this particular bond. When we break it, they both make unstable species. One is much more unstable than the other. So this is the relationship between delta G and ultimately pKa through Ka. If we did all the calculations, we'll get back to this. Let's put another species we've been working with here. Let's put acetic acid. Acetic acid on our relative energy curve looks something like this. Let's just draw its conjugate base up here. It's acetate. This particular energy gap turns out to be 6.5 kcals. After some calculations, this gets us to pKa of 4.75. So the energy gap between acetic acid and acetate is 6.5 kcals per mole. Doesn't mean too much to us, but it translates back into this low pKa. Compounds are becoming more acidic as we go this direction. It's much easier to pull off this proton than this one. And acetic acid or acetate has both induction and resonance. We'll see momentarily why that's the case. We have one more example I want to put on here. It's a new one, so we'll spice things up just a little bit here. We'll take another carboxylic acid. Let's take this acid, and let's put hydrogen, and let's also put a fluorine atom. So on the screen, this should be easy enough to see, but this is acetic acid where we've replaced one of the hydrogens with fluorine. Okay, you should already be predicting right now, as on the quiz today, and we talked a little bit about induction yesterday, what the effect of putting this fluorine in here. As we go to the conjugate base for fluoroacetic acid, is it going to be higher than acetic acid? Is that compound going to be more unstable? Or is it going to be lower than acetic acid, the energy value? Put another way, is this compound more acidic than this one? Or is this compound less acidic than this one? If it's more acidic, the pK will be smaller, the Ka will be larger, the energy gap will be smaller. It turns out for fluoroacetic acid, sorry, my handwriting isn't so great today, but this fluoroacetic acid, conjugate base, maybe this isn't much better. Okay, take a moment and draw this properly. This is the acid and the conjugate base pair, and the energy gap's even smaller. This compared to this is more stable. We have negative charge, and right next door to it, there's nothing stabilizing that negative charge, but right next door in our fluoro case, we have a polar bond. We'll draw this out more in detail in a moment, and partial positive charge here. So this species has additional methods and modes of stabilizing negative charge. It means this gap gets smaller from reactant to product or acid to conjugate base. It means it's easier to pull off this particular proton. It means the pK even lower. In this case, it's 2.7. So it's about 100 times more acidic than this one. pK, 2 pK units is 1 times 10 to the 2 Ka units. So 100 times more acidic.